Okay, so we just got done talking about ionization energy, which is the energy input into a system or into an atom or an element to remove an electron. So we have the opposite of that, which is this concept called electron affinity, and that's the actual energy that's released when an atom absorbs an electron, or an electron is added to an atom, and that creates an anion. So this is the reverse of what we just talked about. Remember, ionization energy was when you had some metal plus an energy makes the cation plus an electron, so we're popping that electron off. Electron affinity is the opposite of that. That's when you have some atom and you add an electron to that and you yield an energy. And so for ionization energy, EI, this is always a positive number, which means it takes energy to remove the electron. That's in contrast to electron affinity, and we're going to call that E sub EA. This is generally, if not always, generally a negative number. And negative numbers of energy, and we'll talk a lot about this in subsequent chapters, the formalism of energy and the perspective of energy, but in chemistry, negative energies means that there's a release of energy upon addition of that electron. So the more negative the value of the electron affinity, there's a greater tendency for that atom or that element to accept the electron or gain an electron. So it's literally the reverse of electron affinity here. So if we take the hydrogen atom for a simple example, the hydrogen atom has an electron configuration, as we know, of just 1s1. So if we want to tack an electron onto that instead of removing it, that's electron affinity. That would create this H- ion. We call that hydride, which would then have an electron configuration of 1s2, right? Because we're adding one electron into that next available shell. And we're going to put on the product side here plus 72.8 kilojoules per mole. And we're adding it on the product side because when we add this electron to hydrogen, we actually get a release. This is a release of this amount of energy rather than putting that energy into the system. And so we would write the E sub EA, or the electron affinity, for this actual reaction is negative 72.8 kilojoules per mole. The negative here implying the directionality of this energy. Negative means heat going out. A positive value would mean that amount of energy was required to go into the system to get the reaction to proceed as written. So this is a release in energy, which means the system is being stabilized because it's decreasing in energy, right? If it's losing energy, it means it started at an energy here and it is lowering to an energy of here, and in doing so, it's releasing that 72.8 kilojoules. Everything in the universe is trying to do this. It's always trying to lower its energy. Anything in chemistry, physics, biology, all things are trying to get to a lower energy state. Once they get lower, that means it's more stable, and that's why that negative here is decreasing, which is a net stabilizing direction for energy to flow. Okay, let's look at another example here. Let's look at neon. So neon is sort of the exception to this rule. What do we know about neon? Well, it's a noble gas. It's already in this nice happy state, right? It loves the fact that it's got a full two shells here, both the 1 and the principal quantum number 2. Nice and happy, doesn't want to add or lose electrons. But if we insist to add an electron to it, Then we're going to create the neon anion, which you've probably never seen before because it doesn't really want to do that. And that means you're going to have to shove an electron into a whole new shell and make this 3s1. Really, really doesn't want to do this. And so, as I mentioned before, generally adding an electron to an atom is going to result in a release in energy, just like we saw for hydrogen. But if you have something that's already super, super duper stable, then adding an electron is actually going to result in an electron affinity that's greater than 0. Remember, negative values are net stabilizing because they're decreasing the energy of the system. Here, we would be going from an energy at this state, and we would be increasing the energy of the system. We'd have a positive electron affinity. That's destabilizing. Okay, so this is all sort of getting you used to thinking about directionality of energy, but also thinking about electron configuration and being able to rationalize why that would be true, right? If we've got a nice happy set of electrons in a closed shell noble gas configuration, trying to jam another electron into it is not going to be good for it. It's not going to like that. That's going to cause the energy of the system to go up. The universe doesn't like that, so that's net destabilizing. So let's look at the periodic table and try to make some general conclusions about what we think the electron affinity energies might look like. Which ones do you think are going to want to accept electrons the most willingly? Which, in other words, would say we'd have the most negative EA. Think about that for a second. Maybe pause the video. Look at what group here on the periodic table is going to be the most negative or the most willing to accept an electron. Hopefully you started to think about potentially this group 7A, which we already know it is only one electron away from being a noble gas configuration, right? If fluorine grabs an electron, that fills up its 2p orbital to be 2p6. It's super happy. And so everything in group 7A, those are going to have the most negative value. Things in group 6A are also going to be pretty willing, but in that case, you're going to need to jam 2 electrons into it to get to the noble gas configuration. What are going to have more positive EA, meaning unwilling to accept an electron, where you really have to force it in, meaning you add energy to the system? Well, we already talked about one example with neon. So anything in the noble gas configuration, those are going to have large positive electron affinities. They don't want to budge. The same is going to be true for things like group 1A and group 2A. Those want to lose electrons, not gain them. So they're going to have large positive electron affinities. Just like we had alluded, if you think back to the ionization energy, we said that these would be the most willing to dump an electron, so they would have low ionization energies. They also then, sort of by the same definition, probably have really high positive electron affinities. They want to get rid of an electron. They don't want to gain an electron. And so the EA or E sub EA and EI are sort of working in contrast to each other. So what does that look like for sort of the periodic trends of the electron affinity? Well, it's much of what we just talked about. So you can see the things that are going to liberate the most energy. By liberate, I mean give off the most energy, which is good. That's a net stabilizing force. You can see we've got fluorine, chlorine, bromine, iodine. So everything in group 7A as we predicted. Those things want to accept that extra electron because that's going to give them that noble gas configuration. We can step back one from each of those, and those would all be the group 6A elements, and so those are going to be the second highest in each case, which makes sense. We're going to have some interesting things that occur down here in this part of the periodic table, which isn't super important here. Really what we're saying is that the important thing to take away in the periodic nature of this particular property of electron affinity, is that as you get closer and closer to achieving a noble gas configuration, then those elements or atoms or ions are going to have a greater likelihood or propensity to accept that electron, which is going to be reflected in a much more negative value for electron affinity.